Scientists just broke physics. The one rule Einstein swore could never be broken was shattered. Faster-than-light travel isn't science fiction anymore, and some of the smartest physicists on Earth think it might actually work. This isn't wishful thinking. This is happening. If you love exploring the cutting edge of science and space, hit that subscribe button and stay with us. Now let's begin. For over a century, the speed of light has been the ultimate cosmic speed limit, a wall that separates us from the stars. At 300,000 kilometers per second, light moves fast, but space is almost incomprehensibly vast. The nearest star system, Alpha Centauri, sits 4.3 light-years away. Even traveling at light speed, which nothing with mass can actually do, it would take over 4 years just to reach our closest stellar neighbor. With current rocket technology, that same journey would consume tens of thousands of years, multiple human lifetimes stretching across generations. But here's where things get fascinating. While nature forbids us from accelerating matter past light speed through normal space, Einstein's own equations offer a loophole. What if instead of moving through space, we moved space itself? This idea isn't new. Back in 1994, a Mexican physicist named Miguel Alcubierre was pursuing his doctorate at the University of Cardiff in Wales. Like many students, he spent Friday nights unwinding with friends, and their show of choice was Star Trek: The Next Generation. Watching the Starship Enterprise zip across the galaxy at warp speed, Alcubierre found himself wondering something most of us never do: could this actually work? That curiosity transformed into equations. Alcubierre sat down and worked through the mathematics of general relativity, Einstein's masterpiece that describes gravity not as a force, but as the curvature of spacetime itself. What he discovered was remarkable. He found a solution to Einstein's field equations that created a bubble of warped space. Inside this bubble, space would remain flat and calm. But around it, space itself would contract in front of the bubble and expand behind it, creating a wave of curved spacetime that carried the bubble forward. The beauty of this concept is profound. You're not actually moving through space at all. You're surfing on a wave of spacetime, and that wave can theoretically travel faster than light without violating relativity's sacred rule. Inside the bubble, you'd experience no acceleration, no crushing g-forces, nothing. You could sip coffee while the universe rushed past outside at impossible speeds. Alcubierre published his paper, and it ignited imaginations worldwide. But there was a catch. Actually, there were several enormous catches that made physicists shake their heads and classify warp drives as beautiful mathematics with no hope of reality. The first problem was energy. Alcubierre's original calculation suggested that creating a warp bubble would require more energy than exists in several times the mass of the observable universe. Not exactly practical for a starship. The energy would need to be negative energy, something called exotic matter, which violates what physicists call energy conditions. In simple terms, you need matter that has negative mass and pushes gravity away instead of pulling it together. As far as we know, such matter doesn't exist in nature. The second problem involved the bubble's interior. Hawking radiation, tidal forces, and other exotic effects would likely make the inside of early warp bubble designs completely uninhabitable. You might reach the stars, but you'd arrive as a cloud of subatomic particles. For 3 decades, these problems seemed insurmountable. Alcubierre's warp drive became a fascinating thought experiment, a mathematical curiosity that showed up in physics papers and science fiction conventions but seemed destined to remain forever theoretical. But here's where our story takes a dramatic turn. Science doesn't stand still. Over the past 30 years, physicists haven't given up. They've refined the mathematics, explored new geometries, and hunted for ways to make warp drives less impossible. And just recently, in the past few months, something extraordinary has happened. In December of 2025, a team of researchers published a paper in the journal Classical and Quantum Gravity that changes everything. The lead author, working with colleagues at a company called Casimir Space, presented what they call an irrotational warp drive solution. Let me break down what makes this so revolutionary. Remember how I mentioned that original warp drive designs required absurd amounts of negative energy? This new design reduces that requirement by a factor of approximately 38 compared to the classic Alcubierre model. Against another competing design called the Notario metric, the improvement is even more staggering, roughly 2,600 times less negative energy needed. Think about that for a moment. We've gone from needing the mass energy of multiple universes to something that's still exotic and difficult, but orders of magnitude more conceivable. It's like the difference between needing to drain an ocean and needing to drain a swimming pool. Still challenging, sure, but suddenly within the realm of imaginable engineering. How did they achieve this? The secret lies in something called irrotational flow. In earlier warp drive models, the space-time around the bubble twisted and rotated in complex ways, creating what physicists call vorticity. This twisting required enormous amounts of energy and created unstable conditions. The new design eliminates that rotation entirely, creating a smooth, curl-free flow of space-time. The researchers demonstrated this mathematically using sophisticated analysis techniques, comparing their irrotational design directly against the older models. When they deliberately added rotation back into their model to test it, the energy requirements exploded again, confirming that eliminating vorticity is the key to making warp drives more physically reasonable. But energy requirements are only part of the story. Another breakthrough addresses the question of whether you could actually survive inside a warp bubble. The new design maintains what's called Hawking-Ellis type 1 stress energy throughout the entire structure. This is a technical way of saying that the energy density behaves in physically reasonable ways everywhere in the bubble, without exotic infinities or singularities that would tear matter apart. Earlier designs had regions where the mathematics broke down, where the forces would become undefined or catastrophically destructive. The new irrotational model avoids these pitfalls. At over 96% of all points they tested in their calculations, the energy conditions could be verified exactly through straightforward mathematics, no ambiguity or undefined behavior. They even included what they call a far-field extrapolation, looking at how the warp bubble behaves at great distances. The results showed that the net proper energy, accounting for both positive and negative contributions, balanced to within 0.04%. That's remarkable precision, suggesting that the design is mathematically stable and well-behaved across its entire structure. Now, another team of researchers tackled the warp drive problem from a different angle, and their results are equally stunning. Instead of creating a continuous bubble of warped space like a sphere around a ship, they designed something that looks startlingly like the starships we've imagined in science fiction. Published in January of 2026, this research presents warp drives built from discrete cylindrical structures they call nacelles, borrowing the term from aviation where it describes the housing around a jet engine. Instead of one smooth, continuous ring of exotic energy, these designs place the energy requirements into separate cylindrical channels positioned around the spacecraft. Imagine a spacecraft with 2, 3, or 4 cylindrical pods arranged symmetrically around it, each one a channel of carefully shaped space-time curvature. Sound familiar? It should. This geometry mirrors almost exactly the nacelle designs we've seen in shows like Star Trek, where engine pods sit on pylons extending from the main hull. But here's what makes this remarkable: these aren't arbitrary aesthetic choices anymore. The mathematics of general relativity actually suggests that this configuration might be one of the most efficient ways to structure a warp field. The researchers, led by Harold White, a former NASA scientist who once headed the experimental Eagle Works laboratory at Johnson Space Center, showed that you can engineer the geometry of a warp bubble like you'd engineer any other vehicle. White has an interesting history with warp drive research. Years ago, while at NASA, he pursued experimental work looking for tiny warp field effects in laboratory settings. His approach was controversial, and the results were inconclusive, but his passion for the subject never wavered. Now, working with Casimir Space, he's approaching the problem from pure theory, refining the mathematics before worrying about hardware. The nacelle design offers several advantages. By localizing the exotic matter requirements into discrete cylindrical structures, you gain flexibility. You can tune the shape of each nacelle independently, adjusting the curvature effects and optimizing performance. The design naturally creates what they call an interior flat region, meaning the space inside your ship remains completely normal, synchronized with the rest of the universe. This solves another major problem with earlier warp drive concepts. In some designs, time inside the bubble would flow differently than time outside. You might travel to a distant star and return home to find that centuries had passed on Earth, even though only months passed for you. The interior flat nacelle design prevents this. Observers inside the bubble remain synchronized with external clocks, experiencing time normally. The research team derived their solutions using something called the ADM formalism, a mathematical framework that breaks spacetime into slices of space at different moments in time. This allowed them to calculate precisely how energy and momentum must be distributed throughout the nacelle structures to maintain the warp field. They created detailed visualizations showing energy density maps, boost magnitude contours, and three-dimensional surfaces representing the shape of the warp bubble. These aren't vague sketches or artists' impressions. They're mathematical constructs derived directly from Einstein's equations, showing exactly how spacetime would curve in these configurations. One particularly elegant feature of the nacelle design is how it handles the transition zones. In the Alcubierre model, the boundary between normal space and the warp bubble is a continuous ring where all the exotic physics happens. In the nacelle model, these transition zones are concentrated at the end caps of each cylinder, like the tips of elongated bubbles. This localization makes the physics easier to analyze and potentially easier to control if we ever build such a device. Now, I know what you're thinking. This all sounds incredible, but we still need exotic matter, right? We still need negative energy, something that seems to violate everything we know about physics. That's absolutely true, and we need to talk about what that means. In classical physics, the physics of everyday objects, energy is always positive. Matter curves spacetime in a way that attracts other matter. That's gravity as we experience it. But quantum physics, the realm of the very small, introduces strange possibilities. Virtual particles pop in and out of existence in the vacuum of space. Under certain conditions, you can create regions where the energy density becomes negative relative to the surrounding vacuum. The most famous example is the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. Place two uncharged metal plates extremely close together in a vacuum, and they'll attract each other. Why? Because the quantum vacuum between the plates has fewer virtual particles than the vacuum outside, creating a region of lower energy density. It's not exactly negative energy in the absolute sense, but it's negative relative to empty space, and that might be enough. The Casimir effect is real. We've measured it in laboratories. The forces involved are tiny, but they're definitely there, confirmed by multiple experiments over decades. This proves that nature permits at least some forms of exotic energy conditions under specific circumstances. But here's the enormous gap between laboratory physics and warp drives. The Casimir effect produces forces measured in billionths of a newton across microscopic distances. A warp drive would need to manipulate exotic energy at scales of meters or kilometers, generating forces powerful enough to curve spacetime around an entire spacecraft. That's not a small engineering challenge. That's a gulf so wide we can barely see across it. Some researchers have proposed other quantum phenomena that might generate negative energy densities. Squeezed quantum states, certain configurations of electromagnetic fields, even the acceleration of the warp bubble itself might contribute to the exotic matter requirements. But all of these ideas remain deeply speculative, backed by mathematics but not by experimental evidence at the necessary scales. This brings us to a crucial point about what these recent breakthroughs actually mean. When researchers say they've developed a warp drive solution that satisfies energy conditions, they don't mean they've eliminated the need for exotic matter entirely. What they've done is show that you can design warp geometries where the exotic matter requirements are minimized, localized, and mathematically well behaved. The April 2024 paper I mentioned earlier, published in Classical and Quantum Gravity, presented what they called a constant velocity physical warp drive solution. The team demonstrated that you could combine a stable shell of regular positive energy matter with a carefully designed shift vector distribution to create a working warp field. The exotic matter is still there, but it's wrapped in a structure of normal matter that helps stabilize the whole system. Think of it like building a bridge. The bridge deck that cars drive on is supported by cables and towers that redirect forces in clever ways. You're not eliminating gravity or the weight of the vehicles. You're managing those forces through intelligent design. Similarly, these warp drive solutions manage the exotic energy requirements through geometric engineering, making them less catastrophically large and more potentially controllable. Another important development came from research into what happens at the boundary between the warp bubble and normal space. A January 2026 paper analyzed the junction conditions where an Alcubierre warp drive spacetime meets regular Minkowski spacetime, the flat, empty space of special relativity. The researchers found that matching these two regions requires the shift vector, the function describing how the warp bubble moves, to satisfy a specific type of equation called the Inviscid-Burgers equation. This is fascinating because Burgers equations show up in fluid dynamics, describing shock waves and turbulent flow. The connection suggests that warp drive physics might have unexpected relationships with other areas of physics, potentially offering new insights or solution techniques. The study also confirmed something important: the warp drive geometry is not globally flat. Even though the interior of the bubble is flat and comfortable, the overall spacetime structure definitely curves. The Riemann curvature tensor, which measures the bending of spacetime, has non-zero components at the joining surface. This means real gravitational effects exist there, distinguishing a warp bubble from simple coordinate tricks that just relabel points in flat spacetime. Why does this matter? Because some critics of warp drive physics have argued that these solutions are just mathematical illusions, coordinate transformations that don't represent real physical effects. This research demonstrates that genuine curvature exists, that these are real solutions to Einstein's equations representing actual curved spacetime, not mere bookkeeping exercises. Let me pause here and address the elephant in the room. Despite all these advances, despite the refined mathematics and reduced energy requirements, we have not built a warp drive. We have not even built a laboratory experiment that convincingly demonstrates warp field generation at any scale. What we have are increasingly sophisticated theoretical models that show such devices might not be completely impossible. That distinction is critical. Physics is full of things that are mathematically possible but practically unreachable. You could, in principle, flip a coin 1,000,000 times and have it come up heads every single time. The laws of physics don't forbid it. But the probability is so staggeringly small that you could wait longer than the age of the universe and never see it happen. Warp drives might fall into a similar category, not forbidden by the fundamental laws, but so extraordinarily difficult to implement that they remain forever out of reach. Or maybe not. That's the beauty and frustration of being at the frontier of knowledge. We simply don't know yet. What we do know is that the theoretical foundation has become substantially stronger over the past few years. Let me walk you through some of the sophisticated analysis that went into these recent papers, because the rigor here is impressive. The December 2025 Irrotational warp drive paper employed something called Cartan Tetrad analysis. Without diving too deep into differential geometry, this is a method of examining spacetime curvature using a specially chosen set of reference frames at each point in space. It's like having a team of observers stationed throughout the warp bubble, each carrying their own measuring devices, all reporting back what they see. Using this framework, the researchers could calculate the stress-energy tensor, the mathematical object that describes how matter and energy are distributed throughout spacetime. They performed high-precision eigenvalue analysis, determining the directions and magnitudes of energy flow at thousands of points in their model. What they found was that the stress energy remained physically reasonable everywhere. There were no infinities, no undefined values, no points where the mathematics broke down. They could trace continuous paths through the warp bubble and see smooth, well-behaved energy distributions throughout. They even stress-tested their design by deliberately introducing vorticity back into the system. Remember, their breakthrough was eliminating rotation in the spacetime flow. By adding rotation back in controlled amounts, they could measure exactly how much damage vorticity does to the energy requirements. The results were striking. Even modest amounts of rotation collapsed the careful balance between positive and negative energy, driving the negative energy magnitude up dramatically. This kind of ablation study, where you systematically remove or modify features to see what breaks, is exactly how good engineering works. You don't just show that your design works. You show why it works by demonstrating that alternative configurations fail in predictable ways. Another research group published a paper in February 2026 focusing on what they call observer-robust energy condition verification. This addresses a subtle but important question: when we say a warp drive violates energy conditions, whose perspective are we using? General relativity teaches us that different observers can measure different things. Someone standing still might see energy flowing one direction while someone moving past sees it flowing another direction. For warp drives, this becomes crucial because the whole point is to create a region moving at exotic velocities relative to outside space. The researchers developed an open-source software toolkit they named Warpax, designed to run on graphics processors for high-speed calculations. Instead of checking energy conditions from just one or a few observer viewpoints, Warpax performs continuous optimization across all possible time-like observers, every possible perspective from which someone could measure the energy. They parameterized the observer space using something called rapidity, a measure of relative velocity in relativity theory, along with the direction of motion. At each point in the warp bubble, the software explores this entire space of possible observers, searching for the ones that would see the most extreme energy condition violations. What they discovered was eye-opening. For the classic Alcubierre metric, if you only check energy conditions from the natural coordinate frame, the frame where the math looks simplest, you can completely miss enormous violations that other observers would see. When they performed the full observer optimization, they found energy condition violations that were orders of magnitude larger than the coordinate frame analysis suggested. Specifically, for the weak energy condition, which roughly says that energy density should never be negative from any observer's perspective, they found violations reaching approximately 90,000 times larger than coordinate frame analysis showed, and this value scaled exponentially with the rapidity parameter. For other warp drive designs, including one called the Rodel metric, coordinate frame analysis missed violations at more than 28% of the grid points they tested. This is a sobering result. It means that earlier assessments of how badly various warp drive designs violate energy conditions might have been far too optimistic. The violations are worse than we thought, requiring even more exotic matter than previous estimates suggested. But here's the flip side: now we know this. We have tools to check energy conditions rigorously, from all perspectives, leaving no hidden surprises. Future warp drive designs can be tested properly from the beginning, ensuring that any claimed improvements are real and not artifacts of choosing a convenient coordinate system. The Warpax study also examined 5 different warp drive metrics: Alcubierre, Lentz, van den Broek, Nacelles, and Rodel, plus an additional warp shell configuration as a numerical stress test. Each represents a different mathematical approach to creating a warp field, with different geometric properties and energy requirements. The Lentz metric, proposed in 2021, uses soliton solutions, wave-like structures that maintain their shape as they propagate. The van den Broek design, from 1999, creates a massive volume of flat space inside a tiny external bubble, potentially allowing a large starship to travel within what appears from outside to be a microscopic speck. The Nacelles metric uses a different shift vector geometry, while the Rodel design incorporates additional mathematical structures to try to minimize energy requirements. By comparing these different approaches under the same rigorous analysis framework, researchers can identify which features lead to better performance and which create problems. It's comparative physics at its finest, treating warp drive design as an engineering optimization problem rather than a single take-it-or-leave-it solution. The geodesic analysis included in these studies is particularly interesting. Geodesics are the paths that freely falling objects follow through curved spacetime. For a warp drive, geodesic analysis tells you how objects and light rays would move in and around the warp bubble. The researchers track tidal forces along geodesics, measuring how much a physical object would be stretched or compressed by the spacetime curvature. They also calculated blueshift and redshift, the compression or stretching of light wavelengths due to relative motion and gravitational effects. These calculations matter for habitability. Even if you solve the exotic matter problem and create a stable warp bubble, you need to ensure that the tidal forces won't tear your spacecraft and crew apart, and that light from the outside universe can still reach you in usable form. Some warp drive configurations create such extreme blueshifting at the forward edge of the bubble that incoming starlight would arrive as deadly gamma radiation. The interior flat design specifically addressed these concerns. By keeping the interior region geometrically flat, you eliminate tidal forces within the habitable zone. Passengers would experience normal gravity, normal time flow, no stretching or squashing forces at all. It's only at the boundary of the bubble, in the nacelles or the shell structure, where the exotic physics happens. Now, let's talk about something that might seem like science fiction even by warp drive standards: faster-than-light communication. A paper from April 2025 explored using photons, particles of light, to transmit information through a warp bubble. The idea is fascinating. If you can create a warp bubble, can you send a signal through it faster than light could travel through normal space? The authors developed a theoretical model where photons encoded with information through polarization and frequency travel within the warped spacetime of an Alcubierre bubble. The photons don't travel faster than light through the local spacetime they occupy. That would violate special relativity. But because the spacetime itself is moving, carrying the photons along with it, the information could traverse interstellar distances in less time than light would need in flat space. From an outside perspective, the signal appears to arrive faster than light, even though locally it never breaks the speed limit. This has profound implications. One of the reasons we assume advanced civilizations haven't contacted us, the famous Fermi paradox, is that interstellar communication at light speed makes conversation impossibly slow. Send a message to a civilization 1,000 light-years away, and you'd wait 2,000 years for a reply. That's not communication, that's throwing messages into the cosmic void and hoping distant descendants might hear back. But if warp bubbles could enable faster-than-light communication, suddenly the galaxy becomes a much smaller place. You could potentially exchange information across hundreds or thousands of light-years in practical timeframes, days or weeks instead of millennia. The researchers calculated how photons would interact with the warp field itself. As light passes through regions of curved spacetime, its frequency shifts, its polarization can rotate, and gravitational lensing can bend its path. All of these effects need to be accounted for and corrected if you want to retrieve the encoded information on the other end. They provided quantitative estimates of these parameters: how much frequency shift to expect, the degree of polarization change, the magnitude of gravitational lensing. These aren't vague hand-waving predictions. They're specific numbers derived from the geometry of the warp field, testable if we ever build such a system. The energy requirements for a communication-scale warp bubble would still involve exotic matter with negative energy density, but potentially much less than a full Starship-scale drive. You're not trying to transport massive cargo or human beings. You're just creating a narrow channel through spacetime for photons to traverse. The geometric requirements might be substantially relaxed. Of course, this remains entirely theoretical. We have no experimental confirmation that warp fields can be generated at any scale, let alone that photons could propagate through them as predicted. But the mathematical framework is there, ready to be tested if the technology ever catches up to the theory. Let me step back and put all of this in a broader context, because I think it's important to understand where warp drive research fits into the larger story of physics and cosmology. Einstein's general relativity has been tested extensively for over a century now. Every experiment, from the bending of starlight during solar eclipses to the detection of gravitational waves from colliding black holes, has confirmed the theory's predictions with remarkable precision. We have overwhelming evidence that general relativity correctly describes how gravity works, how matter and energy curve spacetime, and how that curvature affects the motion of everything from planets to photons. Warp drive solutions are valid mathematical solutions to Einstein's equations. They're not speculation or science fiction added on top of the theory. They emerge directly from the same equations that successfully predict the orbit of Mercury, the gravitational redshift of light climbing out of the Sun's gravity well, and the spiraling death dance of binary neutron stars. But here's the crucial point: just because something is a valid solution to the equations doesn't mean nature actually uses that solution. Mathematics contains infinite possibilities. Physical reality selects from those possibilities based on what actually exists and what can actually happen. An analogy might help. Maxwell's equations, which describe electricity and magnetism, permit the existence of magnetic monopoles, isolated north or south magnetic poles without their opposite partner. The math works fine with monopoles in it. Some theories of particle physics even predict they should exist. But we've never found one. Despite decades of searching, every magnet we've ever examined has both a north and a south pole. The mathematics allows monopoles, nature apparently doesn't use them, at least not in any form we can detect. Warp drives might be similar. The equations of general relativity permit them, but the exotic matter requirements might be nature's way of saying mathematically possible but physically forbidden. Or perhaps not. Perhaps exotic matter exists in forms we haven't discovered yet, or can be manufactured through quantum processes we don't yet understand. This uncertainty is actually what makes the research so valuable. By pushing the mathematics to its limits, by finding solutions that minimize exotic requirements and maximize physical reasonableness, we're mapping the boundary between the possible and the impossible. Even if warp drives turn out to be unreachable, the journey teaches us things about space-time, energy conditions, and the structure of reality that we wouldn't learn otherwise. Several researchers have explored connections between warp drives and other exotic solutions to Einstein's equations. Traversable wormholes, for instance, also require exotic matter to hold them open. A wormhole is essentially a tunnel through space-time, connecting two distant regions through a shortcut that bypasses the space in between. Like warp drives, wormholes emerge naturally from Einstein's equations. The math works. But keeping a wormhole open requires threading it with exotic matter to prevent it from pinching closed, and the energy requirements appear to be enormous, potentially infinite for macroscopic wormholes. Interestingly, some researchers have shown mathematical connections between warp drive geometries and wormhole geometries. Transform the equations one way, and you have a warp bubble moving through space. Transform them another way, and you have a static wormhole connecting 2 points. They're different manifestations of similar underlying physics, both requiring exotic matter, both pushing the boundaries of what general relativity permits. Another connection exists with cosmology, the study of the universe as a whole. Our universe is expanding, and that expansion is accelerating, driven by something we call dark energy. We don't know what dark energy is. We observe its effects, the accelerating expansion, but the underlying mechanism remains mysterious. What we do know is that dark energy behaves like it has negative pressure. It pushes space apart rather than pulling it together. Some cosmological models describe dark energy as a field pervading all of space, and in certain formulations, this field can have properties similar to the exotic matter needed for warp drives. Now, this doesn't mean we can harvest dark energy to power a warp drive. The densities involved are vastly different, and we have no idea how to manipulate dark energy even if we wanted to. But it does mean that nature apparently has no fundamental objection to exotic energy conditions on cosmological scales. The universe itself demonstrates behavior that shares mathematical features with warp drive requirements. This gives some researchers cautious optimism. If the universe can sustain exotic energy conditions across billions of light-years, perhaps there are ways to create similar conditions in localized regions, concentrated and controlled for technological purposes. Quantum field theory, our best description of how particles and forces work at the smallest scales, also permits temporary violations of energy conditions through quantum fluctuations. The vacuum of space isn't actually empty. It seethes with virtual particles, quantum uncertainty made manifest. Under the right conditions, these fluctuations can create transient regions of negative energy density. The Casimir effect, which I mentioned earlier, is one example. Another is something called the dynamical Casimir effect, where accelerating mirrors in a vacuum can create real photons from the quantum vacuum, extracting energy in ways that seem impossible in classical physics. These effects are tiny and fleeting, lasting only moments across microscopic distances. But they prove that quantum mechanics and general relativity, when combined, permit exotic phenomena that neither theory alone would suggest. Some theorists have proposed that the key to generating macroscopic exotic matter might lie in understanding the interplay between quantum field theory and curved spacetime. This field of study, called quantum gravity, remains one of the great unsolved challenges in physics. We don't have a complete theory that unifies quantum mechanics with general relativity across all scales and energies. String theory, loop quantum gravity, and other approaches attempt to bridge this gap, but none have yet achieved definitive experimental confirmation. If and when we do develop a working theory of quantum gravity, it might reveal new phenomena that make exotic matter more accessible, or it might impose additional constraints that push warp drives further into impossibility. This is why the recent mathematical refinements matter so much. By developing warp drive solutions that minimize exotic requirements and maximize physical reasonableness, researchers are creating benchmarks. When quantum gravity theories mature, we'll be able to test them against these benchmarks, asking whether they permit or forbid these specific spacetime geometries. Let me share something that I find particularly inspiring about this research. The scientists working on these problems aren't naive. They know the odds. They understand that warp drives might never be built, that exotic matter might remain forever out of reach, that the universe might simply not permit this kind of technology. But they're pursuing the question anyway, with rigor and creativity, because that's what science is about. You explore the boundaries of knowledge not because success is guaranteed, but because the journey itself expands human understanding. Every paper that refines warp drive mathematics teaches us something new about general relativity, about energy conditions, about the structure of space-time. Harold White, who led the Nacelles warp drive research, has spoken publicly about his motivation. He describes the work as foundational, building the theoretical framework that future generations might need if exotic matter manipulation ever becomes possible. It's planting trees whose shade you'll never sit in, an act of intellectual generosity toward a future we can barely imagine. This connects to something profound about the human relationship with the cosmos. We are a young species on a tiny planet orbiting an ordinary star in an unremarkable galaxy. We've been doing science, real systematic investigation of nature, for only a few centuries. We've had the technology to seriously study the universe beyond our atmosphere for less than a human lifetime. And yet, here we are, working out the mathematics of faster-than-light travel. We're using our minds, evolved on an African savanna to hunt game and gather plants, to explore the most extreme predictions of general relativity. We're asking whether the fabric of spacetime itself might be engineerable, whether the cosmic speed limit might have loopholes. That audacity, that willingness to ask outrageous questions and then actually try to answer them with careful mathematics and rigorous logic, is one of the most beautiful things about being human. Now, I want to address some common misconceptions and questions that come up whenever warp drives are discussed, because separating science from science fiction is crucial here. First, could a warp drive become a time machine? This is a legitimate concern based on solid physics. General relativity doesn't just permit travel through space, it links space and time into a unified space-time fabric. Any technology that warps space might also affect time in ways that could lead to causality violations, traveling backward to before you departed. Some solutions to Einstein's equations permit what are called closed time-like curves, paths through spacetime that loop back on themselves. You could, in principle, travel along such a path and arrive back at your starting point before you left, creating all the paradoxes that time travel stories explore. Warp drives, if they could move faster than light from an external perspective, might create closed time-like curves under certain conditions. This has led some physicists to propose a chronology protection conjecture, the idea that the laws of physics somehow prevent the creation of time machines, perhaps through quantum effects that destabilize any configuration that would permit them. The math here gets extremely subtle. Whether a particular warp drive design permits time travel depends on the global structure of spacetime, not just the local geometry of the bubble. You need to consider the entire universe, how multiple warp bubbles might interact, whether the spacetime topology permits closed paths. Current warp drive research generally focuses on configurations that avoid these time travel issues, treating them as additional constraints that designs must satisfy. But the question remains open, and it's one more way that warp drive physics connects to deep questions about the nature of time and causality. Second, what would you actually see if you were inside a warp bubble? This depends on the specific geometry, but several general features emerge from the calculations. Looking forward, toward the direction of travel, you'd likely see extreme blue shifting of light. Stars ahead would shift toward higher frequencies, visible light becoming ultraviolet and X-rays. The sky in front might glow intensely from radiation that started as innocuous starlight but got compressed by your motion through the warp field. Looking backward, you'd see redshifting, stars fading toward infrared and radio wavelengths, eventually becoming invisible as their light stretched to undetectable wavelengths. The region behind you might appear dark, empty of visible light even though stars are back there. To the sides, perpendicular to your direction of travel, the effects would be less extreme but still strange. Gravitational lensing would distort the positions of stars. Constellations would warp and twist into unfamiliar patterns. You might see multiple images of the same object as light rays bent around the edges of your warp bubble. Inside the habitable region, assuming an interior flat design, everything would seem normal. You'd feel no acceleration, no unusual forces. If you dropped a cup, it would fall normally. If you floated a ball, it would hover as expected. The strangeness would all be outside, in the boundary region where spacetime transitions from the bubble's interior to the normal space beyond. The visual experience would depend on your velocity. At moderate warp speeds, maybe a few times the speed of light, the effects would be noticeable but not overwhelming. At extreme velocities, hundreds or thousands of times light speed, the view might become completely alien, the universe compressed into strange patterns of distorted radiation unlike anything human eyes evolved to interpret. Third, could warp drives be weaponized? This is a darker question, but it deserves consideration. Any technology that manipulates spacetime on the scale required for warp drives would necessarily involve enormous energies, and energy can always be used destructively. Some researchers have calculated what would happen if a warp bubble decelerated suddenly. The energy accumulated in the warp field would have to go somewhere, and the most likely outcome would be a catastrophic release of high-energy radiation from the forward edge of the bubble. This has been colorfully called the Alcubierre death ray in some papers. The amount of energy involved could be staggering, potentially equivalent to multiple stars' worth of output concentrated into a narrow beam. Anything in front of the bubble when it stopped would be vaporized instantly. Planets could be sterilized. Even shielded objects might not survive. This isn't speculation about malicious use. It's a consequence of the physics. Just as a car's kinetic energy becomes dangerous in a crash, a warp bubble's accumulated energy becomes dangerous during deceleration. Any civilization that developed warp drives would need to solve this problem for safety reasons, establishing deceleration protocols far from inhabited systems. The weaponization potential also raises questions about detectability. Could we observe warp drives in operation if other civilizations use them? What would be the observational signature of a spacecraft manipulating spacetime in the ways these theories describe? Several papers have explored this question. A warp bubble would gravitationally lens background light, creating characteristic distortion patterns that might be detectable at considerable distances. The exotic matter in the drive system would have unusual gravitational properties, potentially creating anomalous redshift or blueshift in nearby stars or gas clouds. If warp drives release significant radiation during acceleration or deceleration, we might detect gamma-ray bursts or other high-energy phenomena that don't match natural astrophysical processes. Some researchers have suggested that certain unexplained astronomical transients, brief flashes of light or radiation that don't fit known categories, might warrant investigation as potential technosignatures. This connects to the broader search for technosignatures, evidence of advanced technology elsewhere in the universe. We've spent decades searching for radio signals from alien civilizations, with limited success. Perhaps we should also be looking for gravitational anomalies, space-time distortions, or energy releases that match the predictions of exotic propulsion theories. The irony is delicious. We're using theoretical models of technologies we can't build to predict what we might see if someone else has built them. It's reverse engineering at a cosmic scale, inferring capabilities from consequences we haven't observed but can mathematically predict. Fourth, what about obstacles? Space isn't perfectly empty. Interstellar space contains dust, gas, stray atoms, cosmic rays, all manner of particles and radiation. At ordinary spacecraft velocities, these pose manageable hazards. At faster-than-light effective velocities, even a single hydrogen atom could carry devastating energy. The kinetic energy of a particle goes up with the square of its velocity in Newtonian mechanics, and becomes even more extreme at relativistic speeds. A hydrogen atom hitting your spacecraft at 99% the speed of light carries about 7,000 times the kinetic energy of the same atom at rest. At faster-than-light effective velocities, the numbers become absurd. Warp drive geometries might naturally solve this problem through the same spacetime curvature that enables the motion. The warp field could deflect particles around the bubble, routing them through curved spacetime that keeps them away from the interior region. The math suggests this is possible, but the details depend on the specific design. Some configurations create what amounts to a bow shock, like a boat moving through water, where particles are pushed aside before they reach the bubble's interior. Other designs might absorb particle impacts into the boundary region, dissipating the energy in the exotic matter structure rather than allowing it to penetrate to the habitable zone. This is another area where detailed mathematical analysis is required. You can't just assume the problem will solve itself. You need to calculate geodesics for incoming particles across a range of energies and approach angles, verifying that the warp field deflects them safely. Several recent papers have included exactly this kind of particle trajectory analysis. Fifth, how would you steer a warp drive? This might seem like a trivial question compared to the exotic matter problem, but it's actually quite profound. When you're inside a warp bubble, causally disconnected from the outside universe, how do you interact with spacetime outside to change your direction or velocity? In the Alcubierre model, the shape and motion of the warp bubble are determined by the distribution of exotic matter. To change course, you'd need to reconfigure that distribution, shifting exotic matter from one part of the bubble to another, or changing its density and arrangement. The Nacelles designs offer a potential advantage here. With multiple discrete structures generating the warp field, you could in principle modulate each one independently. Want to turn left? Increase the warp strength on the right side nacelles and decrease it on the left. Want to accelerate? Shift the exotic matter distribution to expand the forward region of the bubble. This resembles how aircraft control surfaces work, or how spacecraft use differential thrust from multiple engines. It's an engineering approach to spacetime manipulation, treating the warp field as a controllable system rather than a static configuration you're stuck with. But the devil is in the details. How quickly could you reconfigure exotic matter distributions? Would there be dynamic stability issues, like an aircraft entering a stall or spin? Could you inadvertently create resonances or oscillations that tear the bubble apart? These questions need answers before warp drives transition from mathematical curiosities to plausible technologies, and researchers are beginning to address them. Several papers from 2025 and 2026 include sections on control theory for warp drives, applying techniques from aerospace engineering and nonlinear dynamics to the problem of navigating through warped spacetime. Sixth, and this is important, would a warp drive actually feel like faster-than-light travel? The answer, perhaps surprisingly, is no. From inside the bubble, you wouldn't feel like you're moving at all. That's the whole point of general relativity. You can't feel uniform motion through curved spacetime any more than you can feel Earth's motion around the Sun or the Sun's orbit through the galaxy. An astronaut inside an interior flat warp bubble would experience weightlessness, just like in orbit. There'd be no acceleration, no force pushing you back into your seat. You could float freely, drink from an open cup, play catch with a ball. Everything would behave exactly as it does on the International Space Station. The only indication that you're traveling faster than light would come from external observations. Looking out your window, assuming the optical effects don't make everything invisible or unintelligible, you'd see your destination approaching much faster than it should. Stars that should take years to reach would arrive in days or hours. When you decelerate and emerge from the warp bubble, you'd find that you've traversed light years of distance in subjective time far shorter than light would need. But you wouldn't have felt any of it. No buffeting, no strain, no sense of incredible speed. Just a quiet float through your ship's interior while spacetime itself did all the work outside. This is fundamentally different from the experience of high-speed travel in ordinary spacecraft, where constant acceleration creates artificial gravity and you definitely feel the forces involved. Warp drives, if they work, would offer the ultimate smooth ride, motion without movement, voyage without velocity in the traditional sense. Now let's talk about energy sources. Even if exotic matter becomes available, you'd still need enormous amounts of ordinary positive energy to create and maintain a warp field. Where would that energy come from? Current human civilization consumes about 18 trillion watts of power continuously. That's 18 followed by 12 zeros, a staggering amount by everyday standards. But it's utterly trivial compared to cosmic energy scales. The Sun outputs about 380 yottawatts. That's 3.8 followed by 26 zeros, dwarfing human energy use by factors of trillions. Early warp drive calculations suggested that you'd need energy equivalent to the entire mass of Jupiter converted to pure energy according to Einstein's famous equation E equals mc squared. Later refinements brought this down dramatically, but even optimized designs might require energy comparable to the output of a large star sustained for days, weeks, or months. No chemical or even nuclear fission reaction could supply this. Nuclear fusion, the process that powers stars, might be marginally sufficient if you could achieve perfect efficiency and had access to truly enormous fuel supplies. More realistically, you'd probably need something more exotic. Antimatter annihilation, where matter and antimatter combine and convert completely to energy, offers one possibility. The efficiency is perfect. 100% of the mass becomes energy. A kilogram of antimatter annihilating with a kilogram of matter would release about 9 times 10 to the 16th joules, equivalent to the largest thermonuclear weapons ever tested, but in a controllable form. The problem is producing and storing antimatter. Current technology can make tiny amounts, individual atoms or small molecules, at enormous cost and difficulty. Storing it requires magnetic or electric fields to keep it from touching ordinary matter and annihilating prematurely. Scaling this up to the tons or kilotons of antimatter a warp drive might need seems impossibly distant with present capabilities. Some speculative proposals invoke zero-point energy, the quantum vacuum energy that pervades all of space. If you could extract energy from the vacuum itself, you'd have an effectively unlimited supply. But zero-point energy extraction faces both theoretical and practical obstacles. Thermodynamics suggests you can't extract net energy from a system in its ground state, and the Casimir effect experiments that do extract vacuum energy produce minuscule amounts. Black hole engineering represents another exotic possibility. Rotating black holes, described by the Kerr solution to Einstein's equations, have an ergosphere region where you can, in principle, extract rotational energy. Drop an object in at the right trajectory, let it split near the event horizon, and one piece falls in while the other escapes with more energy than the original object had. This Penrose process could, theoretically, extract up to 29% of a black hole's mass energy. Imagine a civilization that could create small artificial black holes, feed them matter, and extract rotational energy as needed. Such a technology would make warp drive seem almost quaint by comparison. If you can engineer black holes, you've mastered space-time manipulation at a level that might make exotic matter generation trivial. But we're obviously nowhere near this level. These are thought experiments, explorations of what physics permits rather than predictions of what technology will achieve. Still, they illustrate that the universe contains energy in abundance. The challenge isn't the total amount available but our ability to collect, store, and deploy it in concentrated form. Let me address another fascinating aspect, the problem of creating the warp bubble in the first place. Most warp drive research focuses on the steady-state configuration, the geometry once the bubble is established and moving. But how do you bootstrap it into existence? This is analogous to the problem of getting an airplane off the ground. The steady-state flight is well understood, lift balances weight, thrust balances drag, everything works smoothly. But takeoff is a transition phase with different challenges. You need enough speed to generate lift, which requires thrust against rolling resistance, accelerating mass, overcoming inertia. For a warp drive, you presumably start in normal flat space-time. You need to generate exotic matter or manipulate the quantum vacuum or whatever the mechanism turns out to be, configure it in the precise geometric arrangement required, and somehow transition from ordinary space into the warped configuration. Does this happen instantaneously or gradually? If gradually, what are the intermediate states? Could you get stuck halfway, trapped in a partially formed warp bubble that's unstable? Are there resonant frequencies or critical configurations you need to pass through, like an aircraft approaching and exceeding the speed of sound? Some researchers have studied dynamic warp bubble formation using numerical simulations. They model the exotic matter distribution as a time-dependent field that gradually builds up according to some control protocol. The simulations solve Einstein's equations at each time step, tracking how space-time curves in response to the changing energy distribution. What they found is that bubble formation can be tricky. Too rapid a buildup creates shock waves in the space-time curvature, regions where the geometry changes so abruptly that the mathematical structure breaks down. Too slow a buildup might never reach the critical configuration needed for a stable bubble, like trying to light a fire with damp kindling that smolders but never catches. There appear to be optimal formation protocols that balance speed against stability, ramping up the exotic matter distribution smoothly enough to avoid shocks but quickly enough to punch through any unstable intermediate configurations. These protocols depend sensitively on the specific warp drive geometry, the mass and size of the bubble, and the properties of the exotic matter. This is exactly the kind of detailed engineering analysis that would be necessary for actual implementation. It's not enough to show that a stable warp bubble can exist. You need to show how to create one, how to transition into it from normal space, how to maintain it during flight, and how to safely dissolve it at your destination. The dissolution problem is just as important as formation. When you arrive at your destination, you need to eliminate the warp field and return to normal space. What happens to all the exotic matter? What happens to the enormous energies stored in the space-time curvature? If you just turn everything off suddenly, you get the death ray problem I mentioned earlier, catastrophic energy release that sterilizes everything nearby. Clearly you need a controlled shutdown protocol that dissipates the energy safely, perhaps redirecting it away from inhabited regions or gradually converting it back to whatever form you extracted it from. These aren't showstoppers. They're engineering challenges that would need solutions, problems to add to the already formidable list of obstacles between here and a working warp drive. But they illustrate how much detailed thinking is required beyond the basic solve Einstein's equations and find an exotic geometry level. Let me share something that might surprise you. Warp drive research has practical applications right now, even though we can't build warp drives. The mathematical techniques developed for analyzing exotic spacetime geometries have proven useful in other areas of physics. The Tetrad methods, the observer-robust energy condition testing, the numerical approaches for solving Einstein's equations in complex configurations, all of these find applications in astrophysics, cosmology, and quantum field theory in curved spacetime. Researchers studying the environment around black holes use similar techniques. The spacetime near a black hole's event horizon is extremely curved, and understanding how matter and radiation behave there requires sophisticated analysis methods. Tools developed for warp drive research translate directly to these problems. Gravitational wave astronomy, the detection and analysis of ripples in spacetime from colliding black holes and neutron stars, also benefits. Predicting the waveforms that different astrophysical events produce requires solving Einstein's equations in highly dynamic situations. Numerical methods refined through warp drive studies contribute to this effort. Even quantum field theory on curved backgrounds, used to study everything from Hawking radiation to particle creation in the early universe, employs related mathematics. The challenge of understanding how quantum fields behave in exotic warp drive geometries is fundamentally similar to understanding how they behave near black hole horizons or during cosmic inflation. So the research has value regardless of whether warp drives ever become buildable. It's developing tools, refining techniques, training physicists in sophisticated analysis methods that have broad applicability across theoretical physics. There's also an educational dimension. Warp drives capture the public imagination in ways that, say, tensor calculus on Riemannian manifolds does not. Students who might never consider studying general relativity become interested when you tell them it's the mathematics of faster-than-light travel. The exotic hook draws them in, and they end up learning deep physics along the way. I've seen this firsthand in university courses. A lecture on the Schwarzschild metric might attract polite attention. The same mathematical content presented in the context of warp drives fills the room and generates excited questions. If that excitement leads even a few students to careers in physics or engineering, exploring questions we haven't even thought of yet, the research has served a valuable purpose. Now, let's consider something even more speculative. What would happen if warp drives turn out to be impossible, definitively ruled out by some future discovery? Would all this research have been wasted? I would argue absolutely not. Some of the most valuable scientific work has come from exploring ideas that ultimately proved wrong but taught us essential lessons along the way. The luminiferous ether is a classic example. For decades in the 19th century, physicists believed that light waves must propagate through some medium, just as sound waves propagate through air or water waves through water. They called this hypothetical medium the ether and developed elaborate theories about its properties. The Michelson-Morley experiment in 1887 found no evidence for the ether. Earth's motion through it should have created detectable variations in the speed of light measured in different directions. No such variations appeared. The ether didn't exist. But the search for it wasn't wasted effort. The experimental techniques developed, the precision interferometry required to detect tiny variations in light speed, these became foundational tools for modern physics. The null result led directly to Einstein's special relativity, the recognition that light speed is constant in all reference frames and that space and time are relative rather than absolute. If warp drive research ultimately proves that exotic matter can't exist in the required configurations, or that some quantum gravity effect prevents macroscopic space-time manipulation, or that energy conditions are stricter than we currently understand, these discoveries would be tremendously valuable. They would teach us something profound about the structure of reality, the limits of what's possible, the boundaries within which our universe operates. Understanding what can't exist is just as important as understanding what can. It constrains theories, eliminates possibilities, focuses research in productive directions. If we definitively rule out warp drives, we can stop wondering about them and redirect effort toward propulsion methods that might actually work. Perhaps the research reveals that while warp drives are impossible, some other exotic spacetime structure is permitted. Maybe we can't make traversable wormholes, but we can create stable time-like tunnels with different properties. Maybe we can't contract space in front of a spacecraft, but we can manipulate it in ways that assist conventional propulsion. The landscape of possible solutions to Einstein's equations is vast and largely unexplored. Warp drives are one small region of that landscape. Mapping them thoroughly, understanding why they work or don't work, teaches us about the terrain and where else we might find interesting features. There's also the simple human value of asking what if, and following the question wherever it leads. Pure curiosity-driven research, investigation for its own sake without immediate practical applications, has an intrinsic worth. We are a species that wonders, that questions, that explores ideas because they're interesting. The world would be a poorer place if we only studied things with guaranteed payoffs. Much of our most beautiful mathematics and deepest physics emerged from people playing with ideas that seemed utterly impractical at the time. Number theory was pure intellectual recreation for centuries before becoming essential for modern cryptography. Riemann's work on curved geometry was abstract mathematical play before Einstein realized it was the language of gravity. Warp drive research continues this tradition. It asks bold questions, pushes mathematics to interesting limits, and creates knowledge that might prove valuable in unexpected ways decades or centuries from now. Let me bring this toward a conclusion by discussing the timeline. When might warp drives become technologically feasible, assuming they're possible at all? Any honest answer must acknowledge profound uncertainty. We don't know if exotic matter can exist in the required quantities and configurations. We don't know if the energy requirements can be met. We don't know if quantum gravity effects impose additional constraints. We're essentially asking when we'll develop technologies that depend on physics we don't yet fully understand. That said, we can make some educated guesses based on historical technology development timelines and the magnitude of the challenges involved. In the early 20th century, understanding atomic structure and radioactivity was cutting-edge physics. Einstein's equation E=mc² showed that mass and energy were equivalent and that nuclear reactions could release enormous energy. Within 40 years, humanity had developed both nuclear power plants and nuclear weapons. The timeline from basic physics discovery to technological implementation was measured in decades. Rocketry followed a similar trajectory. The fundamental physics of rocket propulsion, Newton's laws of motion, had been known for centuries. But developing the materials, fuels, and engineering systems to actually build powerful rockets took from the early 20th century experiments of pioneers like Goddard to the Saturn V moon rockets of the 1960s. Again, decades from serious development work to operational systems. For warp drives, we're not even at the basic physics discovery stage yet. We have mathematical solutions to Einstein's equations, but we lack empirical confirmation that the exotic matter they require can exist. We don't have a theory of quantum gravity that might reveal how to manipulate spacetime at macroscopic scales. We're arguably at a much earlier stage than early 20th century physicists were with nuclear energy. If I had to make a wildly speculative guess, I'd say that if warp drives are possible at all, we're probably looking at a minimum of a century before even laboratory-scale demonstrations, and multiple centuries before anything resembling a practical interstellar spacecraft. This assumes several breakthroughs happen along the way. We need a working theory of quantum gravity, experimental confirmation of exotic matter or some equivalent, methods for generating and controlling it, energy sources orders of magnitude beyond anything current, and solutions to all the engineering challenges from bubble formation to navigation to safe deceleration. Each of these could take decades of research. They might need to happen sequentially, each building on the previous one, extending the timeline further. Or they might never happen at all. Some of them might prove impossible, dead ends that force us to conclude warp drives can't be built. But here's what gives me hope: humanity has a consistent track record of achieving things that seemed impossible. We've split atoms, walked on the moon, detected gravitational waves, sequenced the human genome, created artificial intelligence. The impossible has a way of becoming difficult, and the difficult has a way of becoming routine, given enough time and effort. A century ago, quantum mechanics didn't exist as a coherent theory. General relativity was brand new, mostly untested. The idea that we'd have handheld devices containing billions of transistors accessing a global information network would have seemed like pure fantasy. Yet here we are. Who knows what the next century will bring? What discoveries might transform our understanding of spacetime, energy, and the quantum vacuum? What technologies might emerge from physics we haven't even imagined yet? The researchers working on warp drive mathematics today are planting seeds. Maybe those seeds will germinate in a few generations, maybe not. But either way, they're contributing to humanity's long-term project of understanding and eventually, perhaps, reshaping the universe around us. There's something profound about this work that transcends the specific question of whether warp drives will ever exist. It's about refusing to accept that the universe as we find it represents the limits of what's possible. It's about recognizing that we're still in the very early stages of our species' scientific and technological development, that the next 1,000 years might be as transformative as the last 1,000, possibly more so. Let me expand significantly on several crucial aspects that deserve deeper exploration. The philosophical implications of warp drive research extend far beyond the technical details. At its core, this work represents humanity grappling with the cosmic predicament we find ourselves in. We are intelligent, curious beings trapped in a universe where the distances between interesting destinations are almost incomprehensibly vast. Consider the scale problem more carefully. The nearest star system to our Sun, Alpha Centauri, lies about 4.3 light-years away. That means light, traveling at the cosmic speed limit, takes 4.3 years to make the journey. With current spacecraft technology, the trip would take tens of thousands of years. The Voyager probes, humanity's most distant artificial objects, are traveling at about 17 kilometers per second relative to the Sun. At that speed, reaching Alpha Centauri would take over 70,000 years. This creates what some have called the interstellar barrier. Unless we develop radically new propulsion technologies, humanity is effectively confined to our solar system. We might establish colonies on Mars, build habitats in the asteroid belt, mine resources from the moons of Jupiter. But the stars would remain forever out of reach, visible but untouchable, like fruit hanging just beyond grasp. The psychological and civilizational implications are profound. For our entire history, humans have been explorers. We've crossed oceans, climbed mountains, ventured to both poles, and ultimately left our planet to walk on the moon. The idea that exploration might have a final boundary, that there are places we can see but never visit, conflicts with something deep in our nature. Warp drives offer a potential escape from this predicament. If we could manipulate spacetime itself, the distances that seem insurmountable with conventional propulsion might become manageable. A journey to Alpha Centauri could take weeks or months instead of millennia. The galaxy, containing hundreds of billions of stars, could become accessible within a human lifetime. This is why the research matters even in its current highly speculative state. It keeps alive the possibility that the universe is explorable, that the great silence we observe when we search for alien civilizations might not be because interstellar travel is impossible, but because we simply haven't figured it out yet. Let me delve deeper into the exotic matter problem, because this is really the central challenge and it deserves more thorough treatment. When physicists say exotic matter has negative energy density, they mean something very specific and deeply weird. In quantum field theory, the framework that describes particles and forces at the smallest scales, even empty space isn't truly empty. It's filled with quantum fields that fluctuate constantly, creating virtual particle-antiparticle pairs that pop into existence and annihilate almost immediately. These quantum fluctuations give the vacuum a baseline energy density. In most contexts, we can ignore this baseline and measure energies relative to it. But in curved spacetime, the vacuum energy becomes physically meaningful because gravity couples to all energy, including vacuum energy. The Casimir effect demonstrates that quantum vacuum energy is real and measurable. Place two uncharged metal plates very close together in a vacuum. The quantum fluctuations between the plates become restricted because only certain wavelengths fit in the narrow gap. Outside the plates, all wavelengths are possible. This creates an imbalance, a slight pressure pushing the plates together. The Casimir effect has been measured with high precision. It's not speculation or theoretical fantasy. It's real physics, experimentally confirmed. And in the region between the Casimir plates, the energy density is lower than the baseline vacuum energy of empty space. In that specific sense, relative to normal vacuum, the region between the plates has negative energy density. This is exotic matter in a highly constrained, microscopic context. The challenge for warp drives is scaling this up by a factor of perhaps 10 to the 30 or more, creating macroscopic regions with sustained negative energy density sufficient to curve spacetime in the required ways. Several proposals exist for how this might work. One approach involves dynamically manipulating the Casimir effect using rapidly moving mirrors or metamaterials with engineered electromagnetic properties to create larger regions of negative energy density. The mathematics suggests this is possible in principle, but the engineering challenges are staggering. Another approach invokes squeezed quantum states of light. In quantum optics, you can manipulate light fields to reduce uncertainty in one property at the expense of increased uncertainty in another, like squeezing a balloon. Certain squeezed states exhibit negative energy density as measured by specific observers. Could you use this effect at large scales to create the exotic matter a warp drive needs? Then there are proposals involving topological defects in quantum fields, exotic phase transitions that create boundary regions with unusual energy properties, or manipulation of the Higgs field that gives particles mass. Each of these ideas has some theoretical foundation, but all remain highly speculative. The fundamental problem is that we don't have a complete theory of quantum gravity. We know that quantum mechanics and general relativity are both correct in their respective domains, but we don't know how to merge them into a single coherent framework that works everywhere, from the smallest scales to the largest. String theory attempts this unification by proposing that fundamental particles are actually tiny vibrating strings. Loop quantum gravity takes a different approach, quantizing spacetime itself into discrete chunks. There are other proposals: causal dynamical triangulations, asymptotic safety, emergent gravity theories that suggest spacetime isn't fundamental but arises from deeper quantum information structures. None of these theories are complete or empirically confirmed. We lack experimental access to the energy scales where quantum gravity effects become important, roughly the Planck energy of about 10 to the 19th billion electron volts. That's about a billion times higher than energies achievable in particle accelerators like the Large Hadron Collider. This creates a frustrating situation. The physics that would tell us whether exotic matter can really exist at macroscopic scales, whether warp drives are truly possible or forbidden by deep quantum gravity principles, operates at energy scales we can't experimentally probe with current technology. We're trying to map uncharted territory using instruments that can't quite see into the crucial regions. Yet there's reason for hope. Astrophysical observations sometimes provide windows into extreme physics that laboratory experiments can't access. Neutron stars, with densities approaching nuclear levels, test our understanding of matter under extreme conditions. Black hole mergers, detected through gravitational waves, probe the strong field regime of general relativity where curvature becomes extreme. Could some astrophysical phenomenon give us information about exotic matter or quantum gravity effects relevant to warp drives? Perhaps. Some researchers have suggested looking for unusual gravitational lensing patterns that might indicate the presence of exotic matter in cosmic structures. Others propose searching for quantum gravity effects in the polarization of light from distant gamma-ray bursts. These are long shots, but they represent the kind of creative thinking necessary when direct experiments aren't feasible. You look for natural laboratories where the universe itself performs experiments beyond our technological capability, and you try to read the results. Let me expand on the energy requirements more thoroughly, because the sheer scale deserves emphasis and the details reveal interesting physics. When Alcubierre published his original warp drive solution in 1994, initial calculations suggested the exotic matter needed would have negative energy equivalent to the mass energy of Jupiter. That's about 2 times 10 to the 27th kilograms, or roughly 1,000th the mass of the Sun, entirely converted to exotic negative energy. To put this in perspective, if you could convert just 1 kilogram of mass to energy with perfect efficiency using Einstein's equation E equals mc squared, you get about 9 times 10 to the 16th joules. That's roughly the energy yield of 20 megatons of TNT, comparable to the largest nuclear weapons ever tested. Jupiter's mass is about 2 times 10 to the 27 kilograms. Converting all of it to energy would yield about 1.8 times 10 to the 44 joules. For comparison, the Sun's total energy output over its entire 10 billion year lifetime is about 10 to the 44 joules. So the original Alcubierre drive would require exotic matter with negative energy equivalent to the Sun's entire lifetime output, somehow generated and configured appropriately. This is obviously far beyond any conceivable technology. It's not a matter of being a few generations away. It's a requirement so extreme that it seems to place warp drives firmly in the realm of impossibility, regardless of theoretical permissibility. But here's where the story gets interesting. The enormous energy requirement in Alcubierre's original design wasn't an inherent feature of warp drives. It was a consequence of specific choices he made in constructing his solution: the shape of the warp bubble, the thickness of the transition region between flat interior and warped exterior, the velocity profile, and other parameters. Over the following decades, researchers explored how varying these parameters affected the energy requirements. What they discovered was remarkable: the energy needed could be reduced by many orders of magnitude through clever optimization. Chris van den Broek, in 1999, showed that you could dramatically reduce energy requirements by expanding the interior volume of the warp bubble while keeping the exterior small. Imagine a bubble that looks tiny from outside but is spacious inside, like the TARDIS from Doctor Who or certain magical tents from fantasy literature. The mathematical trick involves carefully designed transition functions that create this interior-exterior size mismatch. Van den Broek's design reduced energy requirements from Jupiter mass equivalents down to perhaps a few solar masses, still enormous but orders of magnitude better. Later refinements pushed this further. By the 2010s, some designs claimed energy requirements equivalent to hundreds of kilograms or even less, approaching scales that might be technologically feasible for advanced civilizations. The most dramatic reduction came from optimizing the thickness and shape of the warp bubble's wall, the transition region between flat interior space and the warped exterior. Make this wall too thin, and you need extremely concentrated exotic matter, driving up energy costs. Make it too thick, and the total volume requiring exotic matter becomes prohibitive. There's an optimal balance that minimizes total energy. The shape matters too. Alcubierre's original design used a roughly spherical bubble with front-back asymmetry to create motion. Later designs explored ellipsoidal shapes, toroidal configurations, and more exotic geometries. Each shape has different energy requirements and different physical properties. Harold White's 2012 analysis explored flattening the bubble into more of a disk shape with the spacecraft inside. His calculations suggested this could reduce energy requirements to perhaps the equivalent of a few hundred kilograms of mass energy for a modest-sized warp bubble traveling at 10 times the speed of light. 400 kilograms might seem like a lot, but it's roughly the mass of a small automobile. Converting that mass entirely to energy would yield about 3.6 times 10 to the 19 joules, an enormous amount by everyday standards but perhaps not completely beyond the reach of very advanced technology. More recent optimizations, particularly the work using advanced numerical methods and careful energy condition analysis, have explored even lower requirements. Some designs claim to achieve warp bubble configurations with exotic matter requirements in the tens of kilograms or potentially less. At these scales, warp drives transition from obviously impossible with any conceivable technology to probably impossible with current technology but may be feasible for a civilization a few centuries or millennia ahead of us. That's still speculative, but it's a very different kind of speculation. The key insight is that Einstein's equations permit tremendous flexibility. The space of possible solutions is vast, and we've explored only a tiny fraction of it. Every time someone thinks they've found the minimum energy requirement for warp drives, someone else discovers a new optimization that pushes it lower. Is there a fundamental lower bound? Some theoretical minimum exotic matter requirement below which warp drives cannot function regardless of how cleverly you design them? This is an open question. Some researchers have argued on thermodynamic or quantum grounds that there must be minimum energy costs for traversing space faster than light. Others suggest the requirements might be reducible arbitrarily far with sufficiently clever designs. Resolving this question requires a complete theory of quantum gravity, which we don't have. In the meantime, researchers continue exploring the landscape of possible warp drive geometries, finding more efficient designs and understanding better what trade-offs are involved. Let me discuss the time travel implications more thoroughly, because this connects to deep issues in fundamental physics and philosophy. General relativity permits closed time-like curves, paths through space-time that loop back on themselves so you can return to an earlier moment. These aren't just mathematical oddities. Several exact solutions to Einstein's equations contain them: rotating black holes, infinite rotating cylinders, traversable wormholes, and yes, certain warp drive configurations. The Alcubierre warp drive, if you configure multiple bubbles appropriately, can create closed time-like curves. Imagine two warp bubbles traveling in opposite directions. Set up their paths and timing so they intersect in just the right way. An observer could potentially travel on one bubble, transfer to the other, and arrive back at their starting point before they left. This creates the famous grandfather paradox: you travel back in time and prevent your grandfather from meeting your grandmother, so you're never born, so you can't travel back in time, so your grandfather meets your grandmother, so you are born, so you can travel back. It's a logical contradiction that seems to violate causality itself. Physicists have proposed several resolutions to this paradox. One is the chronology protection conjecture, suggested by Stephen Hawking. The idea is that the laws of physics somehow conspire to prevent closed time-like curves from forming. Whenever you try to create a time machine, something goes wrong, quantum effects create infinite energy densities, the structure becomes unstable, exotic matter requirements become infinite. There's some evidence for this. Calculations of what happens when you try to create a time machine using wormholes show that quantum vacuum fluctuations build up catastrophically, potentially destroying the wormhole just as it's about to allow time travel. Similar effects might plague warp drives configured for time travel. Another resolution is the Novikov self-consistency principle. This says that only self-consistent timelines can exist. If you travel back in time, you can't change the past because you were always part of it. Your attempt to prevent your grandparents from meeting fails in some way you didn't anticipate. The universe enforces logical consistency, allowing time travel but preventing paradoxes. Then there's the many-worlds interpretation of quantum mechanics, which suggests that when you travel back and change the past, you create a branching timeline. You prevent your grandparents from meeting in a different timeline where a different version of you is never born, but your own timeline and existence remain intact. Paradoxes are resolved through timeline proliferation. Each of these resolutions has adherents and critics. We don't know which, if any, is correct because we can't experimentally test them. Building a time machine remains far beyond our capabilities, and natural closed time-like curves, if they exist, are presumably far from Earth in exotic astrophysical settings. For warp drive research, the time travel issue creates both a warning and an opportunity. The warning is that configurations permitting closed time-like curves might be physically forbidden by chronology protection or other mechanisms we don't yet understand. Attempts to build such drives might fail for fundamental reasons unrelated to exotic matter or energy requirements. The opportunity is that studying warp drive time machines teaches us about the relationship between general relativity and causality. By exploring what's mathematically possible and looking for physical principles that might restrict it, we gain insight into the deep structure of spacetime and the laws governing it. Some researchers have suggested that the energy conditions, those restrictions on stress-energy tensors that exotic matter violates, might actually be enforced precisely to prevent causality violation. If true, this would mean that the same physics preventing time travel also sets strict limits on warp drives, even those not configured for time travel. This is speculative but intriguing. It connects the technical question of whether warp drives are possible to fundamental questions about the nature of time, causality, and physical law. These connections make warp drive research philosophically interesting even if it never leads to practical technology. Let me explore the observational signatures of warp drives in more detail, because this has important implications for the search for extraterrestrial intelligence and our understanding of whether other civilizations exist. If warp drives are possible and other civilizations have developed them, we might be able to detect their operation from Earth. This possibility has motivated serious scientific investigation into what signatures a functioning warp drive would produce and how we might observe them. The most obvious signature would be gravitational. A warp drive dramatically curves spacetime in its vicinity. This curvature should produce gravitational waves, ripples in spacetime that propagate outward at the speed of light. When a warp bubble accelerates, decelerates, or changes direction, the changing spacetime curvature should emit gravitational radiation. The frequency and amplitude of these gravitational waves would depend on the specifics of the warp drive design and maneuvers. Formation and dissolution of warp bubbles would likely produce strong bursts. Course corrections might create characteristic modulated signals. A civilization regularly using warp drives in a particular star system might produce a detectable gravitational wave background. Our gravitational wave detectors, LIGO and Virgo, are sensitive primarily to frequencies from about 10 to several thousand Hz, optimized for detecting black hole and neutron star mergers. Warp drives might produce signals at very different frequencies, either much lower or much higher, depending on their operational characteristics. Future gravitational wave observatories might expand our sensitivity. The planned LISA space-based detector will observe lower frequencies, from about 10 to the -4 to 10 to the -1 Hz. Ground-based next-generation detectors like Einstein Telescope and Cosmic Explorer will have improved sensitivity across wider frequency ranges. Between these instruments, we'll have much better coverage of the gravitational wave spectrum by the 2030s and 2040s. If warp drives produce gravitational waves in these observable ranges, we might detect them. Distinguishing warp drive signals from natural astrophysical sources would require identifying characteristic patterns, repeated signals from the same location suggesting regular traffic, modulation patterns inconsistent with natural phenomena, or combinations of frequency and amplitude that don't match known sources. Beyond gravitational waves, warp drives should produce electromagnetic signatures. Remember the Hawking radiation problem? Quantum effects at the boundary between flat interior space and warped exterior should produce particle creation, releasing energy in various forms. For warp drives traveling at apparent velocities much faster than light, this particle creation could be intense. The energy would likely emerge as high-energy particles and electromagnetic radiation across the spectrum from radio waves through visible light to X-rays and gamma rays. The spectrum would depend on the effective temperature of the Hawking radiation, which in turn depends on the steepness of the transition between flat and warped regions. Sharper transitions create higher temperatures and more energetic radiation. The pattern might resemble thermal emission but with unusual characteristics reflecting the exotic geometry producing it. A warp drive moving through interstellar space would interact with the interstellar medium, the thin gas and dust between stars. Even though space is nearly empty, it's not perfectly so. There are roughly 1 million hydrogen atoms per cubic meter in typical interstellar regions, plus trace amounts of helium, dust grains, and other material. A warp bubble moving through this medium at apparent superluminal velocities would create complex interactions. Material couldn't actually overtake the bubble from behind because spacetime itself is being manipulated. But material ahead of the bubble would encounter the warped region moving toward it at incredible speeds. The exact physics is complex and depends on whether you analyze it from the perspective of an external observer or someone inside the bubble. But the general expectation is that interactions between the warp field and the interstellar medium would produce electromagnetic emission, possibly concentrated at the front of the bubble where material first encounters the warped region. This emission might be visible across interstellar distances, appearing as a moving point of light with unusual spectral characteristics. The spectrum wouldn't match a star, planet, comet, or any familiar astronomical object. It would move at speeds inconsistent with ordinary orbital mechanics, potentially crossing light years in days or weeks. Some researchers have suggested that certain anomalous astronomical observations might potentially be signatures of exotic propulsion technologies, though this is highly speculative. Fast radio bursts, brief intense pulses of radio emission from distant galaxies, remain partially mysterious. Most are probably natural astrophysical phenomena like magnetar flares, but could some fraction have artificial origins? Gamma-ray bursts, the most energetic electromagnetic events in the universe, are generally explained by supernova-like stellar explosions or neutron star mergers. But the shortest gamma-ray bursts, lasting less than a second, sometimes have features that don't fit standard models perfectly. Could any of these be related to exotic technology? Almost certainly not, but it's not completely impossible. The point isn't that we have strong evidence for alien warp drives in existing astronomical data. We don't. The point is that if such technology exists and is used regularly by civilizations within our observable volume, it might produce detectable signatures that astronomers could identify once they know what to look for. This connects to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing and the complete absence of evidence for them. If warp drives are possible, the galaxy could be traversed in timeframes short compared to stellar and planetary timescales. A single expanding civilization could potentially colonize the entire Milky Way in a few million years, a blink of an eye in cosmic terms. Our galaxy is over 10 billion years old. Stars with planetary systems conducive to life have existed for most of that time. If intelligent, expansionist civilizations arise with any significant frequency, and if they develop interstellar travel capabilities, we'd expect to see evidence of their presence, megastructures, colonized systems, electromagnetic technosignatures, or direct contact. We see none of this. The sky is silent. No confirmed alien signals, no obvious megastructures, no visits from extraterrestrial explorers. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The impossibility of faster-than-light travel is one potential resolution. If the galaxy is simply too big to traverse with subluminal propulsion, civilizations might be trapped in their home systems or local stellar neighborhoods. The distances are so vast that contact is effectively impossible even if civilizations are common. But if warp drives are possible, this resolution fails. The galaxy becomes explorable, and the paradox deepens. Either intelligent civilizations are far rarer than we estimate, or they don't tend toward expansion, or they do expand but we can't recognize the signs, or we're genuinely among the first. Each possibility has profound implications. If civilizations are rare, we might be nearly unique, bearing special responsibility for the future of intelligence in our region of space. If they're common but non-expansionist, that tells us something interesting about the sociology of advanced intelligence. If they're present but unrecognizable, we need better search strategies. Some researchers have argued that the absence of detected warp drive signatures in our astronomical data constitutes weak evidence against their feasibility. If warp drives were possible and common, we might expect to have seen something by now, an anomalous gravitational wave signal, unusual electromagnetic emissions, something that doesn't fit natural explanations. The counter-argument is that we've barely begun serious searches with appropriate sensitivity. Gravitational wave astronomy only became possible in 2015. Our systematic searches for optical and infrared technosignatures are limited and incomplete. We might simply not have looked at the right places at the right times with the right instruments. Moreover, an advanced civilization using warp drives might do so in ways that minimize detectable signatures, either for efficiency reasons or deliberately to avoid detection. Emission that seems inevitable from our current understanding might be engineered away through technology we can't imagine. Still, the silence is notable. It suggests either that warp drives are rare or impossible, or that our galaxy is less populated than some estimates suggest, or that we need much more extensive searches before drawing conclusions. Let me delve deeper into the engineering challenges that would face anyone attempting to actually build a warp drive, because the technical details reveal just how formidable the obstacles are. Start with the exotic matter generation and containment problem. Suppose you've somehow figured out how to create macroscopic quantities of exotic matter with negative energy density. Perhaps you're using super-advanced Casimir-like effects with precisely engineered metamaterial boundaries, or you've discovered how to manipulate the Higgs field in exotic ways, or you've found some quantum gravity mechanism we haven't even theorized yet. You now face the question of how to arrange this exotic matter in the precise geometric configuration required by your chosen warp drive design. The Alcubierre metric and its variants require exotic matter distributed in a specific three-dimensional pattern around the spacecraft, typically concentrated in a thin shell with carefully controlled density variations. How do you position exotic matter with the required precision? Remember, you're dealing with quantum effects that might be extraordinarily fragile. The negative energy density regions might exist only as carefully maintained quantum states that collapse if disturbed. You need to establish them in the right places and keep them stable while you activate the warp field. This is analogous to some of the challenges in quantum computing, where you need to maintain delicate quantum superposition states while performing computations. Quantum computers are incredibly sensitive to environmental noise, requiring extreme isolation and sophisticated error correction. Now imagine scaling that challenge up to a macroscopic warp field surrounding a spacecraft. You'd probably need active stabilization systems continuously monitoring the exotic matter distribution and making corrections. These systems would need to respond faster than any instabilities could grow, requiring sophisticated sensors and control mechanisms operating at incredible speeds. Then there's the problem of energy supply and distribution. Even with optimized designs that reduce exotic matter requirements dramatically, you still need enormous energy. Creating the exotic matter itself likely requires significant energy input. Maintaining the warp field requires continuous energy. Accelerating and decelerating the bubble requires even more. Where does this energy come from? Current spacecraft use chemical rockets, which derive energy from chemical reactions with energy densities around 10 million joules per kilogram. Nuclear fission offers about 80 trillion joules per kilogram, roughly 10 million times better. Nuclear fusion, if we can master it, might provide a few hundred trillion joules per kilogram. Matter-antimatter annihilation, converting mass directly to energy with perfect efficiency, gives you about 9 times 10 to the 16 joules per kilogram. That's the theoretical maximum for any reaction involving known physics. Even this might not be enough for practical warp drives. You'd need not just the total energy but the ability to deliver it at high power levels, energy per unit time. Creating and manipulating exotic matter might require power measured in terawatts, trillions of watts. For comparison, the entire electrical generating capacity of human civilization is currently around 3 terawatts. A warp-capable spacecraft might need to generate and control power levels equivalent to a significant fraction of Earth's entire energy infrastructure, all contained in a vehicle small enough to fit inside the warp bubble. This demands energy storage and generation technologies far beyond anything currently conceivable. Perhaps you'd use compact fusion reactors, each the size of a desk but producing gigawatt power levels. Perhaps you'd harness zero-point energy from the quantum vacuum itself, if that's even possible. Perhaps you'd use Kugelblitz black holes, Microscopic black holes confined electromagnetically and fed matter to produce Hawking radiation as a power source, a concept so exotic it makes fusion reactors look mundane by comparison. Each of these speculative power sources has its own formidable challenges. Compact fusion requires solving confinement problems that have eluded researchers for decades and then miniaturizing the solution dramatically. Vacuum energy extraction might violate thermodynamics or require manipulating quantum fields in ways that prove impossible. Kugelblitz black holes would need to be created, stabilized, and controlled with precision that seems magical. Beyond power generation, you need energy distribution. The exotic matter configuration creating your warp field is distributed around the spacecraft in a specific pattern. You need to deliver energy to each point in this pattern with precise timing and control. This is like having a three-dimensional grid of millions or billions of energy emitters, each independently controlled with nanosecond precision. The control systems alone would be staggeringly complex. You're essentially conducting an orchestra of exotic matter generators, each playing its part in creating the overall warp field geometry. The timing must be precise because any asymmetry in the field could create unintended acceleration or destabilize the bubble entirely. Now consider navigation. You're inside a warp bubble traveling at apparent velocities potentially thousands or millions of times the speed of light. Your view of the outside universe is severely distorted. Light from ahead is blue-shifted to extreme energies. Light from behind is red-shifted toward radio frequencies. The entire visible universe appears compressed into a narrow band around the equator of your bubble. How do you know where you're going? You can't navigate by starlight in the conventional sense because the optical distortions are so extreme. You might need to rely on navigation systems established before entering warp, following a pre-computed course with inertial guidance. But space isn't perfectly empty. You need to avoid obstacles, stars, planets, asteroids, dust clouds, possibly other spacecraft. At apparent superluminal velocities, you have no time to detect and evade obstacles in your path. By the time light from an obstacle reaches you, you've already hit it, or rather your warp bubble has encountered it. What happens when a warp bubble hits an obstacle? This is a difficult question involving exotic physics. The obstacle can't penetrate the bubble because you're not actually moving through space faster than light locally. But the interaction between the warped spacetime and matter in the path is complex. Some analyses suggest material might be deflected around the bubble, pushed aside by the spacetime curvature. Others suggest it might be caught in the warp field and swept along, accumulating at the front of the bubble. If material does accumulate, it could become a problem. The interaction between normal matter and the exotic matter creating your warp field might destabilize the field or create dangerous energy buildups. Harold White's analysis suggested that particles swept up by a warp bubble might be released upon deceleration as an intense burst of radiation directed forward. This could be hazardous to anything in front of your spacecraft, potentially sterilizing your destination with a deadly gamma-ray blast. Not ideal if you're trying to visit an inhabited planet. This creates a serious safety concern. A warp-capable spacecraft might be an inadvertent weapon, releasing destructive radiation bursts whenever it arrives somewhere. Mitigating this would require additional exotic engineering, perhaps carefully controlled deceleration sequences that disperse accumulated energy safely or warp field geometries that prevent particle accumulation in the first place. Communication presents another challenge. While inside the warp bubble, you're causally disconnected from the outside universe in certain ways. Signals sent from outside might not reach you, or they might arrive severely distorted. Your ability to communicate with home base or coordinate with other spacecraft becomes problematic. You'd probably need to exit the warp bubble periodically to check your position, receive communications, and verify your course. Each exit and re-entry requires deactivating and reactivating the warp field, with all the energy costs and potential risks that entails. Then there's the human factors aspect if you're carrying living crew. What does it feel like inside a warp bubble? Alcubierre's solution is specifically designed so that the interior of the bubble is flat spacetime, meaning crew members experience no unusual gravitational effects. You'd feel normal gravity, normal passage of time, no acceleration forces. But you're surrounded by a shell of exotic matter and intense energy fields. Does this produce radiation that needs shielding? Does it create electromagnetic or gravitational effects that might affect human biology in unexpected ways? Long-term exposure to the exotic physics at the bubble boundary might have consequences we can't predict without better understanding of the underlying mechanisms. There's also the psychological challenge of traveling faster than light. You might look out your window and see the universe compressed into strange patterns, colors shifting in unnatural ways, the familiar constellations distorted beyond recognition. Some crew members might find this disorienting or distressing. The journey time, from the crew's perspective, would be much longer than the apparent travel time. If you're traversing 100 light-years in a week at the apparent velocity, you've averaged about 5,000 times the speed of light. But inside the bubble, time flows normally. The crew experiences a week of subjective time, possibly boring if everything is automated, possibly nerve-wracking if constant monitoring and adjustments are needed. Let me explore the material science challenges more deeply. Every component of a warp-capable spacecraft must function in extreme conditions. The structure holding everything together experiences stresses from the warp field activation and deactivation. Materials at the interface between the spacecraft and the exotic matter field might experience exotic forces we can't currently characterize. You need materials that can withstand high radiation environments, extreme temperatures from waste heat generation, and possibly exposure to exotic forms of energy we don't encounter in normal engineering contexts. These materials must maintain structural integrity and functional properties under all these stresses simultaneously. Current materials science is nowhere near this level. Our best spacecraft materials are designed for relatively mundane stresses, launch vibrations, thermal cycling in vacuum, micrometeorite impacts, radiation from the sun and cosmic rays. These are challenging but well-characterized environments. A warp spacecraft operates in a fundamentally different regime. You might need materials that can sustain their properties while in contact with negative energy density regions. You need thermal management systems that can dissipate waste heat at rates far exceeding anything in current engineering. You need structures that remain stable when the surrounding space-time geometry is being dramatically warped. Perhaps you'd use exotic materials we haven't discovered yet, carbon structures beyond graphene and nanotubes, metamaterials with electromagnetic and gravitational properties engineered at the atomic scale, possibly even matter in exotic quantum states that have useful bulk properties. Some of these materials might need to be manufactured in space using processes impossible on Earth. Zero-gravity fabrication, atomic-scale assembly using sophisticated nanotechnology, possibly even transmutation using particle accelerators to create useful isotopes not found naturally. The manufacturing chain for a warp spacecraft might involve mining asteroids for raw materials, refining them in orbital facilities, fabricating components in specialized microgravity factories, and assembling the final vehicle in a construction dock far from any planet. The entire project could require an industrial infrastructure spanning the solar system. This raises interesting questions about the development pathway toward warp capability. You don't go directly from current technology to warp drives. You need intermediate steps, better propulsion for moving around the solar system efficiently, space-based manufacturing, energy systems far more advanced than current options, and expertise in exotic physics gained through experiments we haven't performed yet. In the end, warp drive research represents something profoundly human: our refusal to accept limits, our determination to explore beyond horizons that seem unreachable, and our willingness to pursue ideas that blur the boundary between science and dreams. Whether warp drives ultimately prove possible or remain forever theoretical, the journey of investigating them has already enriched our understanding of space-time, gravity, and the fundamental nature of reality itself. Every equation solved, every energy optimization discovered, Every thought experiment exploring the consequences of faster-than-light travel adds to humanity's collective knowledge and keeps alive the possibility that the stars might one day be within our reach. Perhaps centuries from now, the first warp-capable spacecraft will embark on its maiden voyage to Alpha Centauri, and its crew will look back at this early 21st century research as the primitive but essential first steps that made their journey possible. Or perhaps we'll discover that the universe truly does forbid such travel, that the cosmic speed limit is absolute and inviolable. Either way, the question is worth asking, the mathematics worth exploring, and the dream worth pursuing, because in reaching for the impossible, we often discover possibilities we never imagined.